Welcome to the Deep Dive. We're the show that takes complex stuff and, well, tries to make it click, giving you those aha moments that actually stick. Today, we're looking at something pretty fundamental, kind of the hidden structure behind almost everything from medicines to, even your own bones. We're talking about chemical compounds. Our mission today is to really get into ionic and molecular compounds. We're using a great resource, Chemistry, an Introduction to General Organic and Biological Chemistry, the 13th edition by Timberlake. We'll try to cut through the usual textbook jargon, really focus on the core ideas, look at how they pop up in biochemistry, and especially how they matter for, health and life sciences. Think of it as your fast track to understanding the molecular world around and inside you. Ready to dive in?
Let's do it. So the foundation for all this really is stability. See, atoms on their own, most of them aren't very stable. They're always striving for that ideal electron setup like the noble gases have. Usually that means 8 electrons in their outer shell. The octet rule, we call it, sometimes 2 for helium. And this whole drive to get a full outer shell, that's what makes them gain, lose, or share electrons when they form compounds. It's all about reaching that stable, sort of happy place.
Right, and that chase for stability, that's exactly how ionic bonds happen, isn't it? You've got metals like, say, sodium or magnesium. They have maybe 1 or 2 electrons hanging out on their outer shell. And it's actually easier for them to just ditch those electrons. That leaves them with a full inner shell, and they become positive ions cations like Na plus or Mg2+ cation.
Exactly. And then you have the nonmetals, chlorine, oxygen, things like that. They're almost there, just short a couple of electrons for their octet. So they're eager to grab electrons, becoming negative ions, anions, SO₄².
So when sodium gives up its electron and chlorine snaps it up, boom.
Pretty much. You get this really strong pull, an electrostatic attraction between the positive sodium and the negative chloride. That's your ionic bond. That's how we get something as common as table salt, NaCl.
It's like a chemical deal where everyone wins, stability-wise.
It is. And what's amazing is how critical this electron shuffle is inside our own bodies. I mean, our whole physiology depends on having the right balance of ions. We're talking Na plus A, K plus A, K2 plus A, Mg2 plus CLL. These aren't just random letters, they're essential.
Oh, right, like electrolytes?
Precisely. Sodium and potassium, for example, they're crucial for managing fluids, nerve signals. You literally couldn't think without them working properly. Calcium, well, everyone knows bones, but it's also key for muscle contraction. Every single movement. Magnesium is a helper for tons of enzymes doing critical jobs, and chloride helps with digestion, keeping fluids balanced. It's a whole system.
Wow. Sounds like a really delicate balance then. What if it gets thrown off?
Yeah, it can cause real problems. Too little sodium, that's hyponatremia, can lead to confusion, even seizures. Too much potassium, hyperkalemia, that can mess with your heart rhythm. Seriously dangerous.
Yikes.
Low calcium, you might feel tingling, muscle cramps. Long term, it contributes to weaker bones, osteoporosis. But the good news is that everyday foods help manage this. Bananas are famous for potassium. Milk, cheese for calcium and magnesium, even potatoes pitch in.
So your diet is literally managing your body's chemistry. That's wild.
It really is.
Okay, so these ions form, they attract each other, and make ionic compounds. You mentioned table salt. What are they generally like, and where else do we bump into them?
Good question. Because of that super strong attraction between positive and negative ions, ionic compounds are usually quite hard. Typically white, crystalline solids when you see them at room temp, and they have really high melting points. Salt, NaCl, melts at 801 degrees Celsius. That's hot. Yeah, it takes a lot of energy to break apart that structure.
Yeah.
They form this repeating 3D pattern, a crystal lattice. Each positive ion is surrounded by negative ones and vice versa. Very stable, very strong.
Okay, so not just salt shaker stuff. Where else?
Oh, everywhere. Epsom salts for a relaxing bath. That's magnesium sulfate.
Huh. Didn't know that.
Antacids for heartburn, often calcium carbonate or aluminum hydroxide, both ionic.
Okay.
Iron supplements often contain iron 2 sulfate. Even your toothpaste might have tin 2 fluoride. It's an ionic compound protecting your teeth.
So they're really hidden in plain sight. Comfort, health.
Exactly. And when we write their formulas, like MgCl2, it's not just random letters and numbers. It shows the simplest ratio of ions needed so that the total positive charge balances the total negative charge. The whole thing has to be neutral, 0 net charge.
Ah, okay. So MgCl2 means 1 magnesium ion, which is 2 plus ions, needs 2 chloride ions, each being 1 to balance it out. 1x plus 2x nev equals 1 equals 0.
You got it. That subscript 2 on the chlorine is crucial. It's like chemical accounting.
Right, makes sense. So we know what they are, why they form, but the names. How do we decipher those labels? Let's start simple. like MgCl2.
For those simple ones, just two elements, a metal and a nonmetal. It's usually pretty straightforward. You just say the metal's name, then the nonmetal's name, but change the ending to "ide."
So magnesium, chlor, U80. Magnesium chloride, easy enough.
Yeah, for many of them it is, but then you run into metals like, say, iron or copper. These guys can be a bit tricky.
How so?
Well, they can actually form more than one type of positive ion. Iron, for example, can lose 2 electrons to become Fe2 plus 2, or it can lose 3 to become F3 plus 2.
Ah, so just saying iron chloride wouldn't tell you which iron ion it is.
Exactly. Ambiguous. So to fix that, we use Roman numerals in parentheses right after the metal's name. F2 plus is iron 2, and F3 plus is iron 3.
Okay, so iron 2 chloride versus iron 3 chloride. Got it. Like specifying the charge.
Precisely. Copper does this too. Copper I is Q plus A. Copper 2 is Cu2 plus A. Lead, tin, several others. There are a few exceptions, though. Metals that only form one common ion, like zinc is always Zn2 plus A. Cadmium is Cd2 plus A. Silver is Ag plus A. For those, you don't need the Roman numeral.
Okay, so if I see a formula, like QCl2, how do I know it's copper 2 and not copper I?
Detective time. You work backwards from what you do know. You know chloride is always Ca, always 1.
Right.
In QCl2, you have 2 chlorides. So that's a total negative charge of 2 times -1, which is -2.
Okay.
Since the whole compound must be neutral, the copper ion has to balance that -2 charge, so it must be Cu2 plus R.
So it has to be copper 2. Copper 2 chloride. That's clever.
It's just logic and knowing those common anion charges.
Okay. Now, speaking of groups with charges, you hear about polyatomic ions. What's the deal with those?
Right. They sound complicated, but the idea is simple. It's just a group of atoms covalently bonded together that as a whole unit carries a charge. Think of sulfate, SO₄². 4 oxygens bonded to a sulfur, and the whole group has a 2 charge. Or ammonium, NH4 plus A, that's a positive one.
So a little team of atoms acting like a single ion.
Exactly. And most of them, interestingly, are anions, negatively charged.
And naming them. Is there a system or is it just memorization?
There are patterns, thankfully.
Yeah.
Often, the most common version of an oxygen-containing ion ends in 8, like nitrate, NO3, or sulfate, SO₄².
Okay, 8 for common.
If there's one less oxygen atom, the ending usually changes to ite. So NO2 is nitrate, SO₄² is sulfite.
8 and ite. Got it. Less oxygen, ite.
For some, especially with halogens, you might even see prefixes. Peri means one more oxygen than the 8 form. Hypo means one less oxygen than the 8 form.
Whoa, okay. Per.8, 8, hypo.ite. That's a system.
It helps. But yeah, there are always a few oddballs you just have to learn, like hydroxide, OH, or cyanide, CNI.
Okay. And writing formulas with these guys. Say magnesium nitrate.
Good example. Magnesium is Mg2 plus Se. Nitrate is NO3, which has a 1 charge. To balance the 2 plus charge of magnesium, you need 2 nitrate ions.
So MgNO32.
Almost. This is where parentheses become essential. If you need more than one polyatomic ion, you put the ion's formula in parentheses, then the subscript outside. So it's MgNO32.
The parentheses keep the NO3 group together and show there are 2 of them. MgNO32.
Makes sense.
Exactly.
It avoids confusion.
And these polyatomic ions, they're not just abstract things either, right? They show up in real life.
Absolutely. We mentioned aluminum hydroxide in antacids earlier. Hydroxide is OH. Magnesium sulfate and Epsom salts. Sulfate is SO₄². Sodium bicarbonate, which is actually sodium hydrogen carbonate, HCO3. That's crucial for pH balance in your body. They're everywhere.
It really drives home how linked this chemistry is to just living.
Okay, so that covers ionic compounds transferring electrons, strong attractions. What about the other side of the coin? When atoms share? Right, that brings us to molecular compounds. Here, instead of a transfer, nonmetal atoms share their valence electrons. They form covalent bonds. This sharing creates distinct individual units called molecules. Water, H2O, carbon dioxide, CO2, classic examples. Even complex things like table sugar, C12H22O11, are molecular.
And this is where organic chemistry comes in too, right? With carbon.
Exactly. Organic molecules are a huge class of molecular compounds based on carbon, usually with hydrogen, oxygen, nitrogen, the building blocks of life. Think about medicines. Aspirin, C9H804, amoxicillin, C16H19N3O5S, Prozac, C17H18F3NO. These are all complex molecular compounds, and their specific structure is key to how they work.
So different way of bonding, different kind of compound. How do we name these? Is it like the ionic ones?
It's actually quite different, mainly because the same two nonmetals can often combine in multiple ways. Look at carbon and oxygen. You can have CO, which is carbon monoxide, or CO2, carbon dioxide. Very different substances, very different properties.
One's famously toxic, the other we breathe out.
Exactly. So the naming system needs to be unambiguous. We use prefixes, mono, dichi, tri, tetra, penta, hexa, and so on, to say how many atoms of each element are in the molecule.
Like counting the atoms. So CO2 is carbon dioxide because there are two oxygens. CO is carbon monoxide for one oxygen.
Precisely, one little rule.
Right.
We usually skip the mono prefix if there's only one atom of the first element, so it's carbon dioxide, not monocarbon dioxide. But we always use mono for the second element if needed, like in carbon monoxide.
Okay, prefixes tell the story. Seems logical. Now, you mentioned covalent bonds, sharing electrons. How do chemists actually visualize that?
That's where Lewis structures come in handy. They're basically diagrams, like little blueprints for molecules. They show which atoms are connected, and they represent the valence electrons as dots. You can see the pairs of electrons being shared between atoms. Those are the covalent bonds. And you can also see any electrons that aren't involved in bonding, the ones that belong to just one atom. We call those lone pairs or unshared pairs.
So you can see the sharing. And sometimes atoms share more than one pair.
Absolutely. They can share one pair, forming a single bond, or two pairs, a double bond, or even three pairs, making a triple bond. Nitrogen gas, N2, has a triple bond between the two nitrogen atoms, for example.
And those simple molecules made of two identical atoms, like N2 or O2 or Cl2.
Diatomic molecules. Yeah, they're great examples of covalent bonding. H2, N2, O2, F2, Cl2, Br2, I2, those 7 naturally exist as pairs. Lewis structures show that sharing clearly.
Okay, but is the sharing always, like, perfectly equal between atoms in a covalent bond?
Great question. Usually no. It depends on the atoms involved. This leads us to electronegativity. Electronegativity is basically a measure of how strongly an atom pulls shared electrons towards itself when it's in a bond. Think of it like magnetic pull for electrons.
So some atoms are greedier for electrons than others?
You could put it that way. There's a trend in the periodic table. Generally, electronegativity increases as you go across a period, left to right, and decreases as you go down a group. Fluorine, up in the top right, is the most electronegative. It pulls electrons really strongly. Cesium, down on the bottom left, is one of philanthropy least electronegative.
Okay, so how does this difference in pull affect the bond?
It determines the type of covalent bond, or if it even stays covalent. We look at the difference in electronegativity values between the two atoms. If the difference is really small, like 0 to 0.4, the electrons are shared very equally. We call that a nonpolar covalent bond. Like in HH or CH bonds, the pull is almost the same.
Okay, nonpolar means equal sharing.
Right. Now, if the difference is bigger, say between 0.5 and 1.8, the sharing is unequal. The more electronegative atom pulls the electrons closer to itself. This creates a partial negative charge, delta minus, on that atom, and a partial positive charge, delta plus plus, on the less electronegative atom. This is a polar covalent bond. It has two poles, like a tiny magnet.
Like in water or HO. Oxygen pulls harder.
Exactly. Oxygen is much more electronegative than hydrogen, so the OH bonds in water are polar.
And if the difference gets even bigger, say more than 1.8,
then the pull is so strong that the more electronegative atom essentially wins the tug of war completely. It yanks the electron away from the other atom that's no longer sharing. It's a transfer of electrons. And that takes us right back to forming ions and an ionic bond, like we saw with Na plus and Cl.
So it's like a spectrum.
Yeah.
Non-polar covalent, then polar covalent, then ionic,
Oh, yeah.
based on how different the atom's electron greediness is.
Precisely. It's a continuum. These differences in bond polarity are super important because they influence the properties of the whole molecule.
Right, which brings us to the molecule's shape. You can have polar bonds, but does that automatically make the whole molecule polar? Seems like shape would matter.
It absolutely matters. This is where VSEPR theory comes in, valence shell electron pair repulsion. It sounds fancy, but the idea is simple. Electron groups around a central atom, whether they're bonding pairs or those lone pairs we mentioned, repel each other. They want to get as far apart as possible to minimize that repulsion.
Like pushing each other away.
Exactly. And how they arrange themselves to maximize that distance determines the molecule's overall 3D shape, its geometry.
So how does that play out? What shapes do we see?
Well, if a central atom has only 2 electron groups around it, like the carbon and CO2, they'll push each other to opposite sides. That's a linear shape, 180 degrees apart.
Okay, straight line. Makes sense. What about three groups?
Three groups. They'll spread out into a flat triangle shape called trigonal planar. Think of H2CO, formaldehyde. The angles are about 120 degrees. But if one of those three groups is a lone pair instead of a bond, the shape you see, based on the atoms, looks bent, like in sulfur dioxide, SO2. The lone pair still takes up space, pushing the bonds.
Ah, so the invisible lone pairs still influence the shape. Interesting. What about four groups?
Four groups is really common, especially with carbon. They arrange themselves in a three-dimensional shape called a tetrahedron. Imagine a pyramid with a triangular base. Methane, CH4, is the classic example. The bond angles are about 109 degrees.
Tetrahedral?
Now, again, lone pairs change the apparent shape. If one of the four groups is a lone pair, like in ammonia, NH3, the atoms form a shape called trigonal pyramidal, like a shorter pyramid.
Still based on the tetrahedron, but looks different because one corner is just electrons.
Right, and if two of the four groups are lone pairs, like in our friend water, H2O,
Yeah.
the atoms end up in a bent shape. Again, derived from that tetrahedral arrangement, so the angle is still around 109 degrees.
So linear, trigonal planar, bent, tetrahedral, trigonal pyramidal. These shapes come directly from electrons repelling each other.
That's the core idea of VSEPR.
And you said this shape is crucial. Why again?
Because shape dictates function, especially in biology. How a drug molecule fits into a receptor site in your body is totally dependent on its 3D shape. It's like a key fitting into a lock.
Okay.
Enzyme activity relies on specific shapes. Even our sense of smell and taste involves molecules fitting into receptors based on their geometry. Life is incredibly shape-dependent at the molecular level.
Wow. So shape determines how molecules interact with biological systems.
Yeah.
Does it also affect how they interact with each other? Like whether something is a solid or liquid?
Absolutely. And that ties back to molecular polarity, which is influenced by both bond polarity and shape. See, a molecule can have polar bonds but still be nonpolar overall if the shape is symmetrical and the bond polarities cancel each other out.
Like CO2. You said it has polar CO bonds, but it's linear.
Exactly. The two polar bonds point in opposite directions, 180 degrees apart. Their poles cancel, like a tug of war ending in a draw. So CO2 as a whole molecule is nonpolar. Same idea with carbon tetrachloride, CCl4, which is tetrahedral and symmetrical.
Okay, so when don't they cancel?
When the molecule is asymmetrical or the poles don't balance. Water is the perfect example. It has polar OH bonds, and it's bent. The poles don't cancel, they add up, giving the whole water molecule a definite negative end near the oxygen and a positive end near the hydrogens. It's a polar molecule.
Same for ammonia, NH3.
Yeah.
Trigonal pyramidal polar NH bonds.
Yep, polar molecule. This overall polarity or lack of it is key.
Because
it dictates the types of forces between molecules, the intermolecular forces, or IMFs. These are the attractions that hold molecules together in liquids and solids.
Ah, not the bonds within the molecule, but the forces between neighboring molecules.
Correct. And the strength of these IMFs determines physical properties like melting point and boiling point. Stronger IMFs mean molecules stick together more tightly, so you need more energy, higher temperatures to pull them apart into a liquid or gas.
Okay, so what kinds of these intermolecular forces are there?
We can rank them roughly by strength. The weakest are called dispersion forces, sometimes London dispersion forces. These exist between all molecules, even nonpolar ones. It happens because electrons are always moving, and sometimes they might momentarily cluster on one side of a molecule, creating a temporary, fleeting dipole. This can then induce a similar temporary dipole in a neighboring molecule, leading to a weak, short-lived attraction.
So even nonpolar things feel some attraction.
Yes, though it's weak. Larger molecules generally have stronger dispersion forces because they have more electrons that can shift around.
Okay, weakest is dispersion. What's next?
Dipole attractions. These occur between polar molecules, the ones that have permanent positive and negative ends. The positive end of one molecule is attracted to the negative end of its neighbor.
Makes sense. Positive attracts negative. Stronger than the temporary dispersion forces.
Generally, yes. Molecules like HCl or PCl3 experience these.
And then, is there something stronger?
Yes, a very important special type of dipole force called hydrogen bonding.
Hydrogen bonding. I've heard of that, especially with water.
Exactly. It's the star attraction for water. Hydrogen bonds happen specifically when hydrogen is bonded directly to a very electronegative atom, nitrogen N, oxygen O, or fluorine F. Because N, O, and F are so electronegative, they pull the shared electrons very strongly away from hydrogen, leaving the hydrogen atom very partially positive, almost like a bare proton. This highly positive hydrogen is then strongly attracted to a lone pair of electrons on a nearby NO or F atom of another molecule.
So it's like a super strong dipole attraction.
Pretty much. It's significantly stronger than regular dipole forces. It's why water has such a high boiling point for its small size. Ammonia, NH3, and hydrogen fluoride, HF, also have hydrogen bonds.
Okay, dispersion, dipole, hydrogen bonds. Is that it for intermolecular forces?
Those are the main types between molecular compounds. But remember, the strongest attractions overall are the ionic bonds themselves within ionic compounds like NaCl. That's why ionic compounds typically have much, much higher melting points than molecular compounds. They aren't just intermolecular forces, they're full charge attractions holding the entire crystal together.
Right, back to that 801 degrees for salt. So it all connects. The type of bond determines polarity. Polarity and shape determine intermolecular forces. And those forces dictate if something is a solid, liquid, or gas.
You've nailed it. From the tiny electron interactions up to the macroscopic properties we can see and touch, it's all driven by these fundamental chemical principles. It makes chemistry feel much less abstract, doesn't it?
It really does. Okay, as we wrap up this deep dive, it feels like we've gone from atoms just wanting stability to building this whole intricate picture of molecules, their shapes, and how they interact.
Yeah, it's quite a journey, from electrons being transferred or shared to the 3D structure and then these forces between molecules.
And understanding these basics, bonding, shape, forces, it really does seem like a key to understanding so much in biology and medicine.
Absolutely. It's foundational. How drugs work, how nutrients are processed, how genetic information is stored and read. It all comes down to molecular structure and interactions governed by these rules. It's the chemical logic underlying life.
So maybe a final thought for everyone listening. The next time you take a pill, or even just taste something, coffee, chocolate, anything, pause for a second, think about the invisible dance of electrons, the specific shapes of those molecules fitting into receptors on your tongue or in your body. Could that precise chemistry be exactly why it works or why it tastes the way it does?
It's a great way to think about it. The elegance of life often boils down to these precise chemical rules.
So keep looking, keep questioning. The chemistry is happening all around you all the time.